Before machines learned to handle symbols, they transformed the scale at which people could move matter, organize labor, and use energy. The Industrial Age did not begin with a single invention, and it did not begin with artificial intelligence. But steam power changed the conditions under which work could be concentrated, timed, and multiplied. At almost the same moment, a proposed calculating engine suggested a different possibility, that a machine might follow a sequence of operations on symbols. One history concerned heat, motion, and production. The other concerned operations, cards, and representation. Their paths were distinct, yet together they made programmable machinery imaginable. A steam engine does not create energy. It converts heat, often produced by burning coal, into mechanical work. Long before steam, people had used water and wind to grind grain, pump water, and move ships. Steam's significance was different. It allowed power to be generated in a concentrated place and carried into mines, mills, locomotives, and workshops. Over time, engines, boilers, shafts, and belts helped reorganize production at new scales. The result was not an autonomous machine world. It was a dense social system of fuel, capital, engineering, transport, wage labor, regulation, and human skill. Factory machinery did change the experience of time. Work that had once been organized around seasons, daylight, households, and local rhythms could now be coordinated around shifts, clocks, production targets, and moving shafts. But the old story that machines simply commanded helpless workers is too simple. Employers, engineers, lawmakers, families, and workers all shaped factory life. People adapted machines, resisted conditions, formed associations, and demanded limits. The factory was not a new temple of pure efficiency. It was a contested environment in which new forms of power met enduring questions. Who controls the pace of work? Who benefits from productivity? And who carries the cost of breakdown? More than a century later, the philosopher Martin Heidegger offered a vocabulary for asking such questions. He called one modern technological mode of revealing Gestell, often translated as enframing. In this mode, things can appear primarily as resources, ready to be measured, ordered, stored, and used. Coal becomes fuel. A river becomes power. Time becomes a schedule. Labor becomes a cost. This is a later philosophical lens, not a word that steam age engineers used. It should not explain every factory by itself, but it helps us notice a danger. When a system sees only what can be arranged, it may stop seeing the lives, landscapes, and purposes that exceed its calculations. The 19th century also explored artificial creation in literature. In the second part of Goethe's Faust, published in 1832, Wagner produces Homunculus through an alchemical process. Homunculus is not an artificial intelligence. He is not a computer, a robot, or a prediction of digital life. He is a peculiar artificial being, luminous, restless, and bound up with questions of form, desire, knowledge, and embodiment. That makes him useful to us, not as a technological prophecy, but as a literary mirror. Goethe stages the strange ambition to make life, and the equally strange discovery that making a form is not the same as understanding what a living being is. A different kind of uncertainty appears in Friedrich Nietzsche's famous phrase, "God is dead," first published in The Gay Science in 1882. Nietzsche was not predicting that machines would replace God. He was diagnosing the erosion of a shared religious and metaphysical framework that had long supplied meaning, authority, and moral orientation in Europe. The question he raises is harder than a slogan. What happens when inherited guarantees lose their force? New sciences and technologies do not automatically answer it. They can expand power, knowledge, and choice, but they can also make the task of judgment more urgent, because no instrument can decide on its own what a society ought to value. While steam power remade physical production, Charles Babbage proposed a machine for a different domain. His analytical engine was never completed in his lifetime, yet its design was remarkable. It separated a mill, where operations could be carried out, from a store, where quantities could be held. It was intended to be directed by punched cards, taking inspiration from the Jacquard loom. This was not a modern electronic computer. It had no microchips, no stored program in today's sense, and no working full-scale implementation. But it offered an architectural idea with extraordinary consequences, a machine whose operations could be specified, varied, and applied systematically. Ada Lovelace entered this story not as a magical lone genius, but as a gifted mathematician working through correspondence, study, and collaboration. In 1843, she published a translation of an article about the analytical engine by the Italian engineer Luigi Menabrea. She added notes longer than the original article. These notes explain the engine's components, cards, and operations in striking detail. They also show something important about historical credit. Lovelace and Babbage worked closely, and historians continue to examine the exact boundaries of their contributions. Her significance does not depend on erasing that collaboration. It lies in the clarity and reach of what she made visible. The most famous part of Lovelace's notes is Note G, a detailed procedure for calculating Bernoulli numbers using the proposed engine. It is often called the first computer program. That phrase captures something real, but needs care. Algorithms existed long before Lovelace, and the famous table in Note G is better understood as a trace of successive operations than as the punched card program itself. Still, the achievement is substantial. Lovelace published one of the earliest detailed computer program-like procedures for a general-purpose mechanical design. She showed how a complex calculation could be broken into ordered steps and followed through a machine architecture that existed, for the moment, only on paper. Lovelace found a beautiful analogy for this possibility. She wrote that the analytical engine weaves algebraic patterns, just as the Jacquard loom weaves flowers and leaves. The phrase does not mean that mathematics is secretly fabric, or that the loom was already a computer. It identifies a shared principle. A structured sequence of instructions can produce a complex pattern. The loom used cards to coordinate threads. The proposed engine would use cards to coordinate operations. In both cases, the material changes, but the deeper idea is recognizable. A process can be represented, organized, and repeated without being improvised anew each time. Lovelace's most far-reaching insight was not simply that a machine could calculate faster. She asked what could happen if relations in music, language, or other domains could be expressed through operations. The engine, she wrote, might act upon things other than number. That did not prove that a machine could understand music or language. It did not demonstrate artificial creativity. The engine was never built, and her examples were speculative. But she had identified a decisive possibility. If symbols can be represented and rules can be specified, a general-purpose machine may operate on more than quantities alone. That is a profound shift from calculation toward computation. Lovelace also drew a boundary. The analytical engine, she argued, has no pretensions whatever to originate anything. It could do what its operations enabled it to do. It did not possess intention simply because its results were complex. This statement later became known as the Lovelace Objection. It remains provocative, but it should not be treated as a final verdict on every later machine. The question is not solved by asking whether a system produces something surprising. Creativity involves more than novelty. It raises questions about agency, purpose, interpretation, and responsibility. A machine can execute a specified procedure. Whether it understands, originates, or creates in a human sense is a different argument. Here, the logic of steel and the poetry of code finally meet. Steam machinery made physical power more available to industrial systems. The analytical engine proposed that operations on symbols might also be arranged, repeated, and varied. Neither development produced contemporary AI. Modern computing required later advances in electricity, electronics, logic, communications, mathematics, materials, and institutions. But the 19th century changed the imaginative horizon. It made it easier to ask whether a machine might not only amplify force, but also carry out a formal procedure. Not only move a load, but transform a representation according to rules. What remained missing was a new medium of speed and connection. Steam could move bodies and goods. Cards could specify a procedure, but symbols still traveled slowly through paper, mechanisms, and human hands. The next transformation would use electricity to carry signals across distance at astonishing speed. Telegraphy, networks, relays, and later electronic circuits would make information itself a new material of coordination. The story ahead is not the inevitable triumph of machines. It is the history of people repeatedly building systems that extend their reach, and repeatedly discovering that extension also changes what they must understand and govern. Steel gave industrial society new ways to mobilize energy. Code gave it a new way to imagine operations. Goethe's artificial being, Nietzsche's crisis of meaning, Babbage's unfinished machine, and Lovelace's notes do not form a single prophecy of AI. They form a field of questions that still matters. What should a machine be allowed to organize? Which tasks can be specified? Which forms of judgment cannot be reduced to a procedure? And when our tools grow more powerful, how do we ensure that efficiency does not become the only language through which we see the world?